Hello guys, how are you today? So today I'll be explaining the physics AMS quiz of term 2 week 9. So let's start with the first question. A loop ABCD is rotating between the poles of a permanent magnet. Which of the following statements are true? Now before we start, I'll just explain a little bit about what's happening over here. So we have that the magnetic field is flowing from the north pole to the south pole. And we know that if it is perpendicular or makes 90 degrees, there is no change in flux. Okay, however, if there is 0 degrees between what? 0 degrees between the magnetic field and the wires, okay, then there is a maximum change in flux. So again, remember, if there's 90 degrees, then there's no change in flux. If it's 0 degrees, then it's a maximal change in flux. Now, let us discuss a little bit about this wire. As you can see, there is this rotating sign over here. That means what's happening is that the current is changing its direction twice every complete rotation. So, every rotation, current changes twice. Okay, keep this in mind. And this is basically all we need to know. And because every rotation the current is changing twice, so it's not a direct current, then it is an alternating current, so it is AC. So let us choose the options. When ABCD is horizontal, the rate of flux through the loop is 0, so let us draw it to be horizontal. It's already given as horizontal. And we know that the magnetic field is from north to south, so as you can see, it's perpendicular, so 90 degrees, so there is no rate of change in the magnetic flux. Okay, now we move on to the next one. The current generated in ABCD is called an alternating current. This is correct. The current through the galvanometer changes its direction twice every complete rotation. This is also true. Now, when ABCD is vertical, the current through the loop is 0. Let us see. When it's vertical, it's going to be like this. And we know it's flowing from the north to the south. And as you can see, with the magnetic field, there is 0 degrees of change. There's like no degrees difference in between them. So 0 degrees means that there is maximal magnetic flux and maximal current. So definitely this is wrong. So the current is going to be maximal and the magnetic flux is going to be maximal. And now finally, the frequency of the generated current is double the frequency of the loop's rotation. This is actually the opposite. Instead, it should be the frequency of the loop's rotation is double the frequency of the generated current. So remember, frequency of the generated current, okay, is half the frequency of the loop's rotation, or the frequency of the loop's rotation is double the frequency of the generated current. From where did we get this? From this. The current will change its direction twice every complete rotation. So just rephrase it. For every complete rotation, you will change the direction of the current twice. So you will generate the current 2 times. We move on to question number 2. Here, what do we need to know from question number 2? Very simply, what we need to know about question number 2 is that the magnitude of the magnetic field, B, is directly proportional to the current, I, okay, that is in the wire, and also the magnetic field, B, is inversely proportional to the distance of the wire. So let's take, for example, this wire over here. If you are gonna do the right hand rule, so your thumb is gonna go up the wire, okay, your fingers are pointing inside, so from this side it is inside, and then it will come outside, so from this side it is outside. Now, the farther the magnetic field, or like the farther the distance the magnetic field from the current, like the less it's gonna be. Same thing with the current, but in an opposite manner. So as you increase the current, then the magnetic field is gonna increase. So it is directly proportional to the current in the wire and inversely proportional to the distance from the wire. We move on to question number 3. They need which of the following are true for a galvanometer. What you need to know is that the more turns a galvanometer has, the more sensitive it is. The galvanometer's loop is placed in a radial magnetic field. The magnetic field will cause a rotating motion, which we call a torque, on the current carrying coil of a galvanometer. Okay, and the smaller the spring constant, the more sensitive the galvanometer is. As well, the greater the magnetic field, the more sensitive the galvanometer is. So in this case, these are the only correct three, whereas for this one, the more turns a galvanometer has, the more sensitive it is. The greater the magnetic field, the more sensitive it is. We move on to question number 4, where we are talking about electromagnets. What we need to know about electromagnets is that how are they made, first of all? Electromagnets look something like this. Usually they have soft iron as their core. So these are called what? They are called conductors, okay? And what we do is that we wind around it. So we make it in the form of a spring. We wind a current carrying wire, okay? Now, electromagnets, what happens is that we send an electric current, and it will go around the soft iron to create a magnetic field. Now, what do we need to know about this magnet, the electromagnet? They are not permanent, they are temporary, meaning that you can stop them anytime you want. You can also increase their strength by increasing the current. You can decrease their strength by decreasing the current. And you can change the direction of the magnetic field by changing the direction of the current. So very simply, over here, this is the first option, that when the current is off, they will stop being a magnet. The second thing is that the electromagnet core is used to increase the magnetic field strength. The next thing is that the direction of electromagnets can be changed at will, whereas they are not permanent magnets and they are not made by winding around an insulating core. They are made by winding around a conducting core. Okay, now here there's probably an equation your teacher taught, which is the magnetic flux through a region. Now, magnetic flux is denoted by phi, like this. It is equal to the product of the magnetic field, B, times the surface area times cosine the angle in between the two planes. Now, usually when we are talking about it in words, we do not say cosine the angle in between the plane. We say the projection of the surface area normal to the plane, or normal to the magnetic field. Okay, so the magnetic flux through region A is defined as the product of the magnetic field, first of all, which is B, magnetic field, and the projection of the surface area, or it's preferable that you write area, not surface area, of the region. So magnetic field times surface area times cosine the angle in between the two planes, or, okay, the region of the area which is perpendicular, or another term is normal to B. So for the first one, it is magnetic field, and for the second one, it is area, and for the third one, it is perpendicular or normal, whichever works. Okay, so now we move on to question number 6. In which of the following electric devices does the current change its sense? To change its sense means that it has it can be positive, then negative, then positive, then negative, like this. This is what the graph is supposed to look like. And by looking at the graph, you can see that it looks like the AC current graph, or the alternating current graph. So definitely, when making an alternating current, we need some specific tools. Okay, these tools are called the slip ring, or another term is the twin ring commutator, but you use slip ring commutator, okay, and then twin ring generator. So it's either slip ring commutator or twin ring generator, or another thing is a simple dynamo. Simple dynamo, because like a dynamo, for example, take in the case of a bicycle, when you pedal your bike, what happens in some bikes, I don't know if all the bikes are like this, but like when you're pedaling, it will turn a light on, and this is what causes the like light to turn on, the motion. So like the current is gonna be moving to turn the light on, and we know that for any light it is an AC a current or an alternating current. Actually, if you want to know a cool trick, okay, try to record your light and then try to put it in slow motion as possible, you'll see that it is flickering, okay? Because the lights, like in a second, they turn on and off up to 50 times. And because like we do not see that it's turning on and off because we are like, our vision or like our sight as human beings, we cannot process this because it's too fast for us to process it. But if you record a video and slow it down, you'll see that the lights are flashing. Or even sometimes when you like record normally, you will see that the lights are flashing, okay? So again, we have a simple dynamo, slip ring commutator, and twin ring commutator. So that means that what does not change its sense has to be a direct current, and directly for the direct current, you are going to put a split ring generator. We move on to the next question. Okay, as you can see, we have two different methods of generating electricity are shown below. Over here, we have a slip or twin ring generator or slip ring commutator. This means that it is an AC current, and if you want to draw its graph, it would look like this. Okay? Here it is a split ring commutator, so if you want to draw its graph, it's gonna look like this because it's a DC current. Okay, now what generator uses an alternating current? It's definitely illustration A because it has a slip ring commutator. And what is in one direction or a direct current? It's definitely generator in illustration B. We move on to question number 8. They're asking us in question number 8. A coil rotated in the presence of an external magnetic field to produce electricity. The output voltage generated in the coil is shown below. When is the surface of the coil perpendicular to the magnetic field? Remember, when we said perpendicular to the magnetic field, then there is no current. Okay, perpendicular to the magnetic field, like in 1, it is no change in magnetic flux or no current. All right, so where is it no current? It has to be 0, so it's at these 3 points. Definitely only choose the labeled one, which are A and C. Moving to the next one, when the surface of the coil is parallel to the magnetic field, parallel means that it is 0 degrees, and we said 0 degrees means maximum current and maximum change in magnetic flux. So in this case, you're going to go to the graph and you're going to choose the maximum. Okay, both maximum like in the positive side and in the negative side. So it's gonna be B and D. We move on to question number 9. Which of the following statements are true about the simple AC generator? Very simply, in an AC generator or an alternating current generator, okay, we said that it can be either made using the twin ring generator or commutator, or the slip ring generator or commutator. Okay, and we know that when we are drawing the graph of the AC, it looks like this. And if you remember from math, this is what? This is a sine function. Okay, so the graph of the AC is a sine function. All right, now in the AC generator, we can have two types of magnets, either a permanent magnet, okay, or an electromagnet. All right, so these are just the important things you need to know about the AC generator, is that it's either slip ring or twin ring. Here, pay attention. It's not split ring, it's slip ring. Now, the current generated varies according to a sine function, like we said. Again, it's either a permanent magnet or an electromagnet, and that is pretty much it. So we move on to the next question, which is question number 10. They said, the peak current in the AC circuit is 20 milliamperes. 20 milliamperes is the peak current. They need the root mean square. How do we find the root mean square? Very simply, you take the peak current, which is 20, and you divide it by radical 2. So in this case, 20 divided by radical 2, you are going to get an answer which is 14.1 to 1 decimal place. So very simply, the answer is 14.1. We move on to the next question, which is question number 11. Consider the device shown in the diagram below. As you can see, we are given a split, not slip, a split ring commutator. That means it is a DC current. A DC current, its graph looks like this. Okay, it looks like a bunch of mountains if you want. So this is the graph I think it's only one option, yeah. This is the graph that describes the current output of this device. We move on to the next question, which is question number 12. Now, this is a very, very nice question. It's about something we took recently, which is transformers. Now, let us draw. We have primary transformer, we have the soft iron, and then we have secondary transformer. Now, what happens is that an alternating current, or an alternating magnetic field, if you want, is going to be flowing through what? It's going to be flowing through the primary current. Let's say primary, secondary, soft iron. Okay? So the alternating magnetic field is going to create an alternating current, or opposite, vice versa. يعني the alternating current will create an alternating magnetic field. Okay? And now what happens? It will go to the soft iron. The soft iron is going to change its path, and it's going to bring it to the secondary coil, which will produce an electromotive force either by increasing the voltage or decreasing the voltage. So very simply, in generating an alternating magnetic field, this is primary coil, helps in linking magnetic field of primary coil with secondary coil, this is soft iron, and then induces an EMF, this is the secondary coil. We move on to question number 13. The transformer, okay, has in its primary coil 760 turns and in its secondary coil 100 turns. As you can see, the number of turns or the number of coils decreased. So if it's decreasing, logically it's going to be a step down. How do you write it? Step dash down, or you can do step space down. It's the same thing. We move on to question number 14. A transformer has 60 turns in the primary coil and N turns in the secondary coil. The peak EMF in the primary and secondary coils of the transformer are 48 volts and 240 volts. Now they need the number of turns in the secondary coil. Keep in mind that the primary coil has 60 turns. So what is the equation we need to follow? It is very simply N2 over N1. So the number of coils in secondary coil, or the number of turns in secondary coil over number of turns in primary coil, is equal to voltage on the secondary coil over voltage in the primary coil. Okay, now only in the case of the 100% efficiency, which is an ideal transformer, which does not exist in real life, so this is never the case, but if they tell you it's an ideal transformer, meaning it has 100% efficiency, then we can apply this rule, which is I1 over I2. Now let us take what's given. We have voltage 1 and voltage 2. Voltage 2 is 240, voltage 1 is 48, is equal to what? Is equal to the number of turns in the secondary, which we need to find, over the number of turns in the primary, which is 60. So you take your calculator and you do cross multiplication. It becomes 60 times 240 divided by 48, and you will get an answer that N2 is equal to 300. Okay? Now, the current in the primary coil is 4 amperes and the current in the secondary coil is 0.72 amperes. They need the input power of the transformer. Input means primary. How do you find power? Power is equal to the current times the voltage. So let us take the primary voltage, which is 48, times the primary current, which is 4. So 48 times 4, it's going to be 192. The output power of the transformer means the secondary. So the secondary voltage is 240. Oops. Okay. 240 times the secondary current, which is 0.72. You put it on the calculator. You're going to get an answer, which is 172.8. You round it approximately 173 watts. Now they need the efficiency of the transformer. What you're going to do is you're going to take power 2, put it over power 1 times 100. So in this case, it is 173 over 192 times 100, and you will get an answer which is approximately 90%. So you are going to put it as 90%. We move on to question number 15. They need us to find the efficiency of the transformer given to the nearest integer. We know to find the efficiency, it's power 2 over power 1. So power 2, how do you find it? It is 110 times, pay attention, 162 milliamperes. So 162 times 10 to the power of minus 3. You are going to get 17.82 over 2.2 times 9 volts, which is 19.8, and then multiplied by 100. So 17.82 over 19, this is 9, not 4, 19.8 times 100, we will get it approximately to be 90 degrees. So the answer is 90 degrees. We move on to question number 16. Now, an AC supply is used to light a bulb with the same brightness as does a 12 voltage battery. Now, they did not tell us it is the peak, okay? And what we know is that the AC supply is used to light the bulb with the same brightness as the 12 voltage battery. So the 12 voltage battery is now our root mean square. So to one decimal place, the root mean square is 12.0 volt. Now to find the peak voltage, we know that the equation of a root mean square is equal to the peak voltage over radical 2. So to find the peak voltage, it's gonna be the root mean square, which is 12 times radical 2. On the calculator, 12 times radical 2, it is 16.9. To one decimal place, you can keep it 16.9, or you can round it to be 17.0. So very simply, 17.0 is an answer. We move on to question number 17. Now, what is generated in the coil when the coil rotates relative to the poles above? First of all, by looking, you can see that there's only one current, or no, there's two types of current. There's the alternating current and there's the direct current. So let us see. What type of current is generated in the coil when the coil rotates? Directly, when you see rotation, it is alternating current, okay? It rotates relative to the poles of a magnet, because the magnet is the only thing with poles, okay? And then finally, okay, and now finally the current is taken out of the rotating coil through either twin ring commutator or a slip ring commutator. Okay, so very simply, alternating current, then it is a magnet, and then it is twin ring commutator. We move on to question number 18. In question number 18, they said the front screen of an oscilloscope is imprinted with a grid. The horizontal scale has units of what, and the vertical scale has units of what? What you need to know, very simply, horizontal is this, and horizontal is always the time. Vertical is this, and vertical is always the voltage. So very simply, the horizontal is always the time, and the vertical is always the voltage. So horizontal is time, vertical is voltage. We move on to question number 19. It states, if a secondary coil has more turns than a primary coil, then the transformer is called a, pay attention, N2 is greater than N1. That means it is a step up transformer. So step dash up, or you can write it as step space up. We move on to question number 20. They said, when the transformation ratio is less than 1, the transformer is called a what transformer? The transformation ratio, which we denote by nu, so like nu as in something new, I don't know how to write it like this, something like this. Just say n like this, okay? It is equal to n2 over n1. So if n2 over n1 is less than 1, that means what? That means n2 is definitely less than n1. And if n2, which is the output, is less than the input, that means it is a step down transformer. We move on to question number 21. An ideal transformer has primary and secondary coils of 160 and 4,800 turns respectively. Respectively means that this one is for primary, this one is for secondary. The AC voltage at the output of the secondary coil is 270 volts. They need us to find the voltage of the input. Very simply, the rule is N2 over N1 is equal to V2 over V1. N2 is 4,800 over N1, which is 160, is equal to voltage 2, which is 270 over N1, which is X that we need to find. You do cross multiplication and you will end up with 270 times 160 divided by 4,800, and you will get an answer of 9 volts. So our answer is 9 volts. We move on to question number 22. The diagram below shows a wire carrying a current directed rightwards placed in a magnetic field directed inside the plane of the picture. They need to find the electromagnetic force. What is the right-hand rule? The right-hand rule, you're going to take your thumb, your index, and your middle finger. The thumb is how the current flows. Your index is the direction of the magnetic field. And the middle is the direction of the electromagnetic force or the electromotive force. Okay, so the thumb in this case, our thumb is going to follow the current I, which is going to the right. Then our index is going to be pointing inwards, so towards the tablet. And finally, the middle finger is going to be pointing upwards. Please don't take it as something bad, even though it is something bad. But like, it's going to be pointing upwards. So that means the electromagnetic force is pointing upwards, so it is directed upwards. We move on to question number 23. As you can see over here, we are shown what? We are shown a DC electric motor. How do we know it's a DC electric motor? Because there are no rotations. If you are to see a rotation like this, something like this, like we saw in question number 1, then it is an AC electric motor. But here in this case, since there's no rotation, then it is what? A DC electric motor, a direct current. It has only one direction. Now, the side A of the coil experiences. Again, how do you find the direction of the electromagnetic force? They're telling us this is the north face, this is the south face, okay? From A, it is flowing like this, so our thumb is going to be following the flow of the current. Then our index goes with the direction of the magnetic field, which is from north to south. So it's going to be pointing like this. And then, so your thumb is going to be pointing kind of down or towards the left. Then your index is going to be pointing to the right. And then if you put your middle finger perpendicular, you are going to get it to be upward, so it's an upward magnetic force. We move on to question number 24. The input voltage in the ideal transformer is 12 volts. The number of turns in the primary coil is 100 turns. The number of turns in the secondary coil is 650 turns. Now pay attention, they said what? An ideal transformer. Now, when they ask us ideal transformer, that means we can use the equation I1 over I2 is equal to V2 over V1 is equal to N2 over N1, but in this case, I don't think they will ask. So, they need the output voltage of the transformer, very simply. N2 over N1 is equal to V2 over V1. So, 650 over 100 is equal to x over 12. You're going to do cross multiplication. You get 650 times 12 over 100. So you will get 78 volts. This is the output voltage. Now, as you can see over here, based on the numbers of turns of transformer, it was 100, then it became 650. So it's increasing. That means it is a step dash up transformer. We move on to question number 25. Okay, so now here this is a little bit tricky. They need the efficiency of the transformer up to the nearest integer. We know efficiency is power 2 over power 1 times 100%. Now, power is voltage times the current. And since we are not given the voltage, we need to use another way. We are given the number of turns, so we know N2 over N1 is equal to V2 over V1. N2 is 50 over N1, which is 300, is going to be equal to V2 over V1. So what we could do is we could just substitute. You could take V2 as 50 and V1 as 30. So now you have V2 to be 50 times current 2, which is 27 milliamperes, which is 10 to the minus 3 amperes, over 300, which is voltage 1 multiplied by 5 milliamperes, which is 5 times 10 to the power of minus 3. Now, you're going to put it on your calculator. You're going to get an answer of 9 over 10 multiplied by 100, and you will get 90% efficiency. So, as you can see, based on the number of turns of the transformer, it was 300 turns. It became 50 turns. So, it's decreasing. So, it is then a step down transformer. we move on to question number 26, which is the final question. Okay, question number 26. Choose the correct answers to complete the sentences describing the function of a transformer. A step-up transformer, definitely, that means that N2 is greater than N1, and that means V2 is greater than V1. That means that the voltage of the power source is gonna increase, so it increases a voltage of a power source. An ideal transformer, means what? It means power 2 over power 1 times 100 is equal to 100, and that means power 2 is equal to power 1. So that means an ideal transformer does not change the output power because power 2 is equal to power 1. Whereas a real-life transformer decreases the output of power because you never have an ideal transformer. That means P2 is always less than P1. So that means the output power is always less than the input power. So it always decreases the output power because why? Some of the energy is lost due to heat or is dissipated as heat. Now finally, if a transformer increases output voltage, it is definitely going to decrease output current. So think of it like this. Power is equal to voltage times current, and the power remains constant, okay? So let us say the power is staying the same, it is constant. If the voltage is increasing, then definitely the current needs to decrease because they are on the same side of the equation. That means they are inversely proportional. That means as you increase the output voltage, you are going to decrease the output current. So let's submit and hopefully we don't have any mistakes. And thank God we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day.